Hey guys, here is a scenario. We've got a cart of mass M is attached to an ideal spring that can stretch and compress equally well. The natural length of the spring without the cart is at point E. The cart and the spring rest on a smooth angled track. The cart is pulled to position A, so down here, and then released. The cart then moves toward position E, where it reverses direction and returns again to position A. So a few important things here is the natural length of the spring is at point E. So what that means is right here, it shouldn't have any elastic potential energy at that point E there. So they're going to give us a chart here that they want us to fill out, and we've got to come up with the different amounts of energy in each case here. So notice over here, let's focus on this first. They say it's a sketch the energy bar charts for the cart, spring, earth system. So when we include earth, remember we can talk about gravitational potential energy. The spring is what allows us to talk about spring energy here. And then the cart is going to contain kinetic energy when it's moving. Right here at point E, when it's at its maximum height, and it has no spring energy, and it shouldn't be moving for a moment in time, then that is all gravitational potential energy there. And there's 16 joules of it, or 16 whatever units of it. So that's the key here. We've got to have a total of 16 units of energy the whole time due to conservation of energy. So that means down here in the bottom, notice they've already said down here at point A, so down here, it's all the way at the bottom of the ramp, and it's got no gravitational potential energy and no kinetic energy because it's not moving. So all of it must be, and I don't know if that's actually 16 bars or not, that's about it. So all 16 joules of it must be in the spring energy there. Now the other thing to think about is gravitational potential energy is the easiest to deal with. And the reason for that, and we're going to come back to that, is that gravitational potential energy is mass times gravity times height, or an h if you want to write that. And so it's just directly proportional. So as we continue to increase our distance up here, like B, or C is twice as far as B, and E is 4 times as far as A, we will just go up by equal increments. So here, if you look at it, we've got 1, 2, 3, 4 units up to the top. That's 16. So that must mean at B, when we only went up 1 unit, we must have gone only up a fourth. So I'm going to estimate that that is about 4 units of potential energy here. C, we went up halfway, so that makes sense. We should have 8 joules compared to the 16 joules over here, because we're halfway up the hill. And then when we're at point D, that's 3/4 of the way up, and so I don't know if that's actually 12 bars. I'm not going to take the time to count it, but let's just say it is. That should be 12 units of energy there. So what about here now we've got the potential energies in there, so now the kinetic energies, let's look at them. Well, this one's easy. We've got to have a total of 16. 9 of it is in spring energy, 4 of it is in gravitational potential energy. That gives us 13, so another 3 of it must be in kinetic energy. Over here, 12 of it is in gravitational potential energy, 1 of it's in spring energy, that's 13, so we also must have 3 of it in kinetic energy there. So what about C there in the middle? This is where we need another little bit of information, another equation. Remember that the potential energy due to a spring is 1/2 kx squared. So if we only have half our stretch length, as opposed to all of it, half gets squared, and we only have a fourth of our spring energy. So here, all 16 joules are spring energy, but here, when we're only stretched out half as much, we should only have a quarter of that. So 1/4 of it should be spring energy. And again, that comes from here. If we plugged in a half into x, then because that gets squared, we only get a fourth of our energy out. We've got to have a total of 16, so 8 of it is gravitational, 4 of it spring energy, that's a total of 12. That means our final bar here for kinetic energy, that has got to be another 4 to get us up to the total there. All right, let's look at these questions here. And by the way, they say write a narration explaining what you did. We sort of talked through why we filled in the bars the way they did. Do the energy bar charts depend upon whether the cart is moving left, down the track, in other words, or right up the track? No. All of those things only depend upon position. So they only depend on position. So the position affects the gravitational potential energy and the spring energy, and everything else is left over to kinetic. And by the way, kinetic, the velocity gets squared, so it wouldn't matter if it was positive or negative. So no is the short answer there. Part D says, as the cart moves from A to E, the total energy of the system should be the same at each labeled point. Explain why this is the case, and if it's not, fix it. Well, conservation of energy is the reason. So now we should say what is required to make conservation of energy work for a system. You might be like, oh, it always works. Well, it works in the universe. But to make it work in a system, we need no outside forces. Because if we have an outside force, then we will have work being done, and that will change the kinetic energy of the system. But we don't have any outside forces, so no work done, no change in kinetic energy, which would then translate into energies of the other types as well. Part E here says, as the cart moves from A to E, the gravitational potential energy should increase by the same amount between each labeled point. Explain why this is the case. Well, we sort of already did. Gravitational potential energy is mass times gravity times your height. So it is proportional to your height. Double your height, double your gravitational potential energy. And then finally, part F, as the cart moves from E to A, the spring potential energy should increase quadratically. Explain why this is the case. Well, we kind of already did. The spring energy is equal to 1/2 k x squared. So spring energy is proportional to x squared. Double your distance that you've stretched, 2 squared is 4 times the amount of spring energy there.